we have Piotr Kowalski from the University of Wroclaw talking about model theory of fields.
Thank you very much for the invitation and for coming. I'm not sure if my voice is going, it's okay. Thanks a lot. Okay, so I made several assumptions. One of them was that you all know what is a ring or field. This may be not true, but I will mostly have a very specific examples of ring or fields, like and this I assume you do know, like integers, rational numbers, reals, complexes. Just for a while we will talk about matrices. And also about finite field of n elements. And then, as you may know, n has to be a power of prime. So in the talk I will try to give some actually one basic notion from model theory of fields and rings. It will be all about definable sets. What are they in particular structures? How do they look like? Can we classify them? And how are they related to some of them are open mathematical problems. And these problems are quite easy to state, so you can even try to solve them on your own. I tried once without any success. But first I have to say, this will be a bit formal, but not too formal. What are the formulas? Always in the ring language. So we compose them from variables. They are usually denoted x, y, z. Then from logical symbols, like quantifiers for all exists, and connectives like or and not anything else. And one important, equality. And then we have ring symbols. So this is plus, minus, times, 0, and 1. So all the rings today will have 1. So I just give you examples of formulas. So you should compose formulas in a meaningful way using all these symbols and possibly brackets. For example, you can say y equals x times x. You can say x times y equals 1. Or you can say something using quantifier exists z such that y minus z equals x squared. So note that here, all the time, this x and y are kind of free, and the z is bounded by this quantifier. So such formulas we will denote. We want to point out what are those free variables, not bounded by any quantification. So far it means nothing. This is just a sequence of symbols. It will get a meaning when we look at a particular ring and try to understand what do they mean inside this ring. Okay, so far it is just a sequence of symbols. Okay, some more examples. You can say exists y, x equals y square. You can say that x is 0 or x is 1. Or you can say something strange, that x is 0 and x is 1. So here all the time we have one free variable. So such a formula, you know, p of x. And another type is when there are no free variables, everything is bounded. So you can say for all x, for all y, x times y equals y times x. Or you can say things like for all x, x plus x equals 0. Or you can say 1 plus 1 equals 0. And here, no free variables. And formula which has no free variables is called a sentence. Okay, so far it's maybe not very interesting. They are just string of symbols. So let us see now what is their meaning in some particular structures. So now if we have ring and sentence, then we can check if the sentence is true or not in this ring. And if it is true in R, it will be denoted like this. So here we have the sentences. So let's check if they are true or not in some of these examples. So of course, this sentence just says that ring is commutative. xy is always yx. So in R, this is true. Because this is commutative ring. And just for this occasion, I put this one, which is not commutative. So in this one, it is not true. So negation is true. And about this sentence, when 1 plus 1 equals 0, it is true, for example, if the field has two elements. So we have 2. It is true. And then it is even true in F2 that for all x, x plus x equals 0, there are not too many x's. But for example, in F3, it is not true. Here 1 plus 1 is 2, which is not 0. Okay. So if we have such a sentence, something which has no free variables, and we have a ring, we can check whether it's true or not. Now what we can do if free variables do appear, now R is a ring and Px is a formula with one variable, then for any R in R, we can put this R in place of X and then get a sentence, and then we can check if it's true or not. So now let's test this sentence and the ring. So for example, if R is the field of real numbers, phi is this sentence, this formula. It's better if I say y times y. Square was not a part of the language. Then if I take R, for example, equal 4, then exists y such that 4 equals. So of course, it is true in R, we can find such a y, which is 2. And similarly, all positive numbers have squares in R, but it's not true that -1 is a square. Okay, so if we have a sentence with 1 free variables, for some elements of our ring it is true, on some elements of our ring it is not true. And this is actually how we define a definable set. So in this, phi of big R will be the set of all the small R in R, such that in R phi is true when little x is replaced with this R. So in this example, and this is called definable set. So in this example, for which R, phi of R was true here, it's easy to see that only for non-negative R's, only non-negative numbers, only non-negative real numbers have square roots. So for equal this, the corresponding definable set is the set of non-negative numbers. So this is an example of a definable set in reals. Okay, so that's my main point in this lecture. Discuss definable sets in different string and fields, and some open questions related to them. Let's see some more examples. Okay, we have this formula. Now we have arbitrary and formula saying x is 0 or x is 1. So what does it define? It obviously defines the set 0, 1. Now let's take a formula of x is x equals 0 and x equals 1. What does this define? What are elements in the ring which are both 0 and 1? What do you think? Huh? Yes, almost always. So, phi of r, where by trivial you mean empty, and I agree. Some people like to talk hours about empty sets, but I'm not one of them. I will talk 5 seconds about empty set. So this is, let us start what is not empty. It may happen that it is the entire ring, if the ring is the 0 ring, and only then. Or it is empty, otherwise. So, not a very difficult exercise to show that if 0 equals 1, then your ring is 0 ring. Okay, and the same. I will just say briefly. Same for formulas with 2 variables. Now they define, they give definable sets. But now we plug 2 elements, so definable sets in R squared. So for example, we have this one. Y. So we know very well what does it define. It's a graph of the function y equals x squared. So it defines a parabola. We are in the reals, let's say. If we have such a formula. It defines hyperbola. And if we have this more complicated one, what can this formula define? When does it happen that y minus x is a square? If you think a little, it happens if and only if y minus x is non-negative, which happens if and only if y is greater or equal than x. So this formula defines an order, the order from R. X is more equal than y. If and only x is so yes, so formally order is a subset of R squared, and it can be defined by this formula. So it's also a definable set. So now let's look what kind of sets are always definable. Okay, so my problem here for a given ring R, describe or classify definable sets. R. Example if it is related to different parts of mathematics. If this is algebraic closed field, it's related to algebraic geometry. If this is ring of reals, it's related to real geometry, etc. Okay, and we focus on one variable, simplicity. So always finite sets are definable. I mean, as the one here, by the same way we could define any finite set. So similarly, complements of them, called cofinite sets, are definable. The complement is just defined by negation of this. And for some rings, this is all. So now we consider to the end of this lecture for particular cases. First one, you may think that R is C, complex numbers, or any algebraically closed field. Algebraically closed means that any non-constant polynomial has a root. This is true for complex numbers and for some other fields. Non-constant polys have roots. So the theorem here is that in such a case, only it is obvious. Focus on one variable case. Obviously, in two variables, you can always define diagonal x equals y. So, okay, so of course, Chevalier did more. You know these terms. He showed that image of constructible set is constructible, and this is a very special case of this. Constructible subsets of well, K are just finite cofinite.
So when we define an arbitrary finite set, so we include this constant signature also part of the language.
Ah, that's a good point. I was purposefully skipping. For as formally, if you have a structure, if you have a ring, you extend the language by constant symbol at all elements. This I didn't want to get into, but yes, you are right. Yes, you have to, definitely you have to include parameters. Without these parameters, you would get something like rationals, for example.
Things you can produce with the
And yes, the rationals, the prime field you would get. Elements of finite elements of prime field. So if a field has such a property that only finite and cofinite sets are definable, then such field is called minimal. So in short, this theorem says that algebraically closed implies minimal. So of course, if a mathematician sees an implication, we want to invert it. And there was a conjecture. Somebody a bit less famous, made it in 1973. So if you don't mind, I will just write this. Can we have implication thus minimal implies algebraically closed? Turns out to be not so easy. So just in 2000, Wagner answered affirmatively, but only in positive characteristic. If characteristic is 0, it is still open. So you can try to do it at home. Take a field of characteristic 0. Imagine that whatever you do, no matter what kind of formula you construct in one variable, it always defines finite or cofinite set, nothing else. Show that it must be algebraically closed. We don't know. Yes, open means here not proved, and we don't even know the answer. Maybe it's not true. Maybe there are fields which are not algebraically closed of characteristic 0, and still we can define only finite or cofinite sets. So that was about case 1. Sorry, yes? Good point. Yes. So let me state, yes, you are very right. I was sloppy. Conjecture infinite. In model theory, we tend to ignore finite structures, although I put it before. But yes, of course, we have to assume finite are trivially minimal in this sense. But pseudo-finite are that was first case. So second case, consider field of reals. This is obviously not minimal. We notice that this interval, which is obviously not finite, neither cofinite, is definable. Okay, but then also you can see that each interval is definable. And this is basically it. So now Tarski showed he didn't phrase it this way, but in today's terminology R is all minimal. That means minimal like here, but up to order, which means each definable set, always in one variable we are talking about, is a finite union of intervals or points, singletons or points. You can think about point as an interval as well. Nothing else. So finable sets look something like this. So intervals of points, closed or open, infinite or not infinite. This is typical definable set. So in these two cases, definable sets are taught at least in one variable, are very easy and fully understood. In the last two cases I will talk about, they are pretty wild and they cannot be even understood. It is understood that they cannot be understood. So it's something. So third case, R is Z. Okay, let's focus on the following question. Is a set of integers definable in Z? So you can think for a while when I erase the board with this little pink. Okay, so of course natural numbers are the positive elements in Z. But the formula which defined positive, non-negative real numbers will not work here. But if Px same formula, then what we get in Z? We get squares in Z, and there are much less of them than all natural numbers. So P of Z this is of course much smaller than n. So this formula doesn't work, but maybe some other formula works. And actually it was known even in 17th century that it does, and proved in 18th. There is Lagrange four-square theorem. It says that each natural number is a sum of four squares. Still fine. I say exactly 4 because you can always add 0 square. Yes, looking at 7, you see that you need at least 4, but the theorem is 4 are enough. So now if you put such a formula, a bit longer. So let me put squares to lose too much time. Then it's okay, it defines n Z. So this also means that order is definable in Z because x is smaller or equal than y if and only if y minus x is in n. So this also becomes definable. And that actually implies, looking at things like Peano arithmetic, that there are many definable subsets in Z, and there is no way to classify them. So basically, if we notice that if we are able to think of integers somewhere, then there is no hope to classify definable sets. They become extremely complicated. This is related to, okay, some of them are given by Diophantine equations. So let me just show the most famous one. If x, y, z defines this Fermat, defines an equation. Okay, then now we know what are the solutions. Okay, for n equal to, it's very classic, you get Pythagorean triples. And what is extremely untrivial, for higher n, you get only the trivial solutions. So if I put all of them correctly for n equal 3, you get only those. And then similarly trivial. And of course this is the content of Fermat's last theorem. Which was finally proved by Weiss. It has nothing to do, well, not much to do with model theory, but this is another example of definable sets. But it has a bit to do with something else. So probably you heard that in 1900, David Hilbert suggested how many? 19 or more problems, and one of them is related with these issues. This is Hilbert's 10th problem. So the hope was, okay, the question was, can you find algorithm where you are given, you find an equation like this, so a special formula, algorithm will tell you it has a solution or not. So find an algorithm deciding if a defined time equation has a solution. Yes, in these terms, as I said, if some special, actually existentially definable set, okay, if some special existential formulas define empty sets or non-empty sets. And the answer was, of course, well, we don't know such an algorithm, so most likely it doesn't exist. And indeed, Matyasiewicz answered no. I was checking yesterday, it was in 1970, but I didn't know it was in his PhD thesis, and he was just 23 years old when he did it. Okay, I still have some time, so this was about that. The last structure I want to discuss in terms of definability is the field of rationals. Here the main issue is, as I said, if we can define Z somewhere, it becomes extremely complicated. So here main problem is Z definable in Q. And this was answered So the answer is yes, but the formula is so complicated I cannot show you. How does it look like? Actually, I don't think they really show formula, they just say how to define it using some quadratic forms. So first, Julia Robinson. Answered yes. So again, Q is very, very complicated in terms of definable sets, and they cannot be classified. So more precisely, she showed that there is such a formula just show the shape of it. First, it has twice universal quantifier. Then it has 7 times existential quantifier. And then it has 6 times universal quantifier again. And then finally we get some polynomial over Z. Okay. This only 3 variable t, and all of those appearing before. So formula is in such a shape. This is polynomial over Z. There is such a polynomial, such that such a formula defines exactly Z inside Q. Not something immediate at all, how to define Z inside Q using only plus times and all these logical formulas. Then people, so this is Julia Robinson, then people wanted to simplify it, and the story continued for quite some time. And in 2009, showed that one quantifier, we can kill this block of quantifiers. So there is for all exist. formula. Same. Here's 2 universal and 7 existential. Some other polynomial, of course. So how far one can continue? We cannot reduce all the quantifiers, but recently one more block of quantifier was reduced, and this becomes related again to Hilbert's 10th problem, but now over Q, not over Z. So finally, Etkinliğimizin in 2016 his Atlas paper showed that there is just a universal formula such as P of Q. So now this phi looks something like this. But he doesn't specify how many universal quantifiers. Now not zero. This is again some poly. So I finish saying how this is related to some version of Hilbert's 10th problem. And there will be one more open question. This is related with something called Hilbert's 10th problem. Over Q. Maybe I just stated in a cheating way that take a Hilbert's 10th problem and replace Z with Q. So it asks if you can find an algorithm telling if polynomial equation, many variables, has a root over Q or not. So now the thing is, if we could find an existential definition of Z in Q, this would have negative answer. So if one finds an existential formula phi of x defining Z in Q, then no Hilbert's 10 or Q. But this is still open. This we don't know. Yes. This is open question. Which I guess may be stated in a simpler way. So just, is there a polynomial over Q either over Z or over, okay, maybe over Z, maybe over Q.
Is it the same?
No. you know, it says, okay, maybe if I define this, I will discuss the difference, okay? So the question is there a polynomial like this, such that for all AQ, or maybe this formula okay, so why it's not the same? If you negate it, if you take negation of this formula, then you get exactly such a formula. So it means what Koenigsmann did, he showed that the complement of Z in Q is of such a form. But it doesn't imply that Z is of such a form. Okay? Those are called Diophantine set. This is like projection, actually. It's like projection of Q points of algebraic variety. So the question is, if you want, is there an algebraic variety over Q such that projection of it on Q is exactly Z? This is open. What Koenigsmann showed that there is such that projection is exactly the complement of Z in Q. It's not the same. Apparently there is a way from this. One can somehow easily get this, but not the other way. Okay, so second question you can flip at home. Let's check some polynomials if they give you Z in Q like this. Okay, if you have some free time. Thanks for your attention.
Any question?
I have one.
Yeah?
Can you give an example of a formula that gives I in C in complex numbers?
Just I?
Just I.
Well, okay, but maybe that's the issue he mentioned. The example is x equals I.
But I is not a
That's exactly what he said. I was cheating a bit. I allow parameters from C.
Yeah, I love the parameters from the ring.
I allow the parameters for the ring. I didn't want to get into this. Without this, I could not. Of course, the formula x squared equals -1 would give you this set you were probably thinking about. But we do allow parameters, yes.
So the theorem of Tarski about real numbers, is the proof real algebraic geometry?
This was this elimination procedure. I think he was considering real ordered fields. It's more, I'm not sure, but I would say it's more like real algebra. I think it was some kind of algebraic proof and rather formal. Maybe it has something to do with real algebraic geometry. I'm not sure.
What I want to ask is, okay, if there is another question in R, do we do real algebraic geometry? And when there is that, do we do number theory and algebraic geometry?
It goes both ways, but usually what people do, if, for example, it is true if you add, usually if there is anything about R, first what people do in model theory is check whether it is ominimal or not. Like, for example, if you add exponential function, it is still ominimal. And if it is ominimal, there is general machinery with some geometric flavor, some cell decompositions, etc., which give you lots of information. So it rather goes this way. Some general model theoretic formalism, I guess, inspired by real. But if you then have a particular question, then all the methods somehow come together, hard to put them apart. Okay, but for example, if you want to show Hilbert-Stellensatz, they are separate. They are proofs purely geometric, purely algebraic, and purely model theoretic. All different proofs.
Purely model theory.
Purely model theoretic, yes, you can. Yes. They all need to know. All you need to know is to know that there is only one. If you have big cardinal number, then there is only one algebraically closed field up to isomorphism of this cardinality. This is the only algebra you use to prove Hilbert-Mischel results using model theory. It's hard to answer. Yes, good point. I was just thinking about it tonight. More difficult way, just use n. Okay, but easier way, actually you can see that you can define, it's also true in Q, that each, or each x you can do it using normal Lagrange four-square theorem. Just complete the denominator to square and do it. So by this, you can define, this defines, if you have this, you can define order, yes, because so I guess this is the easiest way. You can also define natural numbers using this Trianopison theorem and say that positive rationals are n over n, where both are natural, but this is more difficult. This should be the easiest. Yes, because then it would define, is it easy to say? It's definitely true. Okay, so you can show, going a bit further, you can show that all definable sets in any power of C are constructible, so come from Zariski closed. If you know, they come from polynomial equations over C, maybe some unions and complements, and then you have to see that complex conjugation is not like this. That's one of the ways, maybe something easier. I guess in 10 minutes I would be able to find easier proof, but definitely it can be done. It shouldn't be difficult.
Another question? That's my next speaker again.
General theorems say that you cannot define any order. It's maybe some difficult to define the order.